It's fascinating. It really is. Um, in your book, you speak about how there was a time when people looked at our universe and they imagined a sort of clockwork, deterministic structure ticking away that we're kind of just embedded into and kind of run through. Um, and then you kind of talk about how in the 20th century, this was really heavily challenged, especially by reference to chance and uncertainty. I thought it'd be great just to get you to touch on those key notes for us.
Yeah, yeah. This is another aspect of why and how the history of probability is particularly fascinating, and how things have evolved and developed, how our understanding has grown. Um, in many ways, I think it's an advance comparable with the uh, Einstein's discovery of relativity and the development of quantum theory and so on. Um, so pre-20th century, let's take that as a sort of convenient date. Pre-20th century thinkers made huge advances in our understanding of nature. I'm thinking of Newton and so on. And that was in terms of causes and effects. From simply observing that, for example, if you threw a rock and it went up and down before hitting the earth, we learnt how to describe the rock's motion in mathematical terms. And understanding those sorts of relationships meant we could make steam engines, petrol engines. It opened up the unlimited capabilities of electricity, for example. And we really thought we'd got it. Indeed, around the turn of the 19th to 20th century, many scientists thought that little fundamental remained to be discovered. There are lots of quotes to this effect. It was just a question of working out the consequences of the laws which had been discovered. Although there were one or two lingering anomalies, but it was thought, just iron them out, just work out the details. In general, people were very confident that those lingering anomalies could be resolved. But the fact is, of course, that resolving those lingering anomalies led to complete revolutions in our understanding. It led to, relativity, quantum theory, and, for example, later it led to chaos theory. Completely different ways of looking at things. So, quantum theory, for instance, tells us that right at its very core, nature is random. You can't predict it. It's not a question of measuring things more accurately or of simply finding the right things to measure. It's fundamentally unpredictable. Indeed, I'm sure you're familiar with this. The Heisenberg principle, Heisenberg uncertainty principle, says that certain pairs of measurements are mutually incompatible. The more accurately I measure one of them, the less accurately I can't measure the other one, so accurately. The more accurately I measure the position of a particle, the less accurately I'm able to measure its momentum, for example. Chaos theory illustrates another way in which probability and uncertainty are fundamental. You might think that you could predict how a tossed coin would fall if you could measure the details of how it was flipped carefully enough. Maybe you build a machine which does it very precisely. After all, we understand all the equations relating the force of the initial toss and the way the coin's rotating. That's the essence of the clockwork universe. I can tell you how this coin is going to, how it's going to fall if I've got sufficiently precise details of how I flip the coin in the first place. Give me the starting point in sufficient detail, and I can work out what the end point will be. That's the clockwork universe, the pre-20th century universe. But there are some weasel words in there. I said sufficient detail. Now, I can measure the initial conditions as accurately as you want, but I can never measure them infinitely accurately. I can measure them at 10 decimal places. I can measure them at 20 decimal places. But if a difference in the 11th or 21st or 31st, whatever, decimal place leads to a different outcome, then the outcome's a chance event. I can't predict it. There's a physicist called Michael Berry, an eminent physicist, who gave a beautiful illustration of this. He showed that the gravitational effect of the movements of two players around a pool table is enough to change the movements of the balls very, very slightly. Incredibly, I don't know how many decimal places, slightly. But that infinitesimal change will amplify over the collisions of the balls, because when two spherical balls hit, if they're in a slightly different place, they bounce off a very different angle. And the movement of the two players around the pool table will amplify over repeated collisions of the balls. so as to completely alter their angle of deflection after just 9 collisions. This is I'm sure you're familiar with this. It's the butterfly effect, but that's the butterfly effect in action. So you know, the point is, pre-20th century clockwork universe, we knew what was going on. We could predict what would happen if we knew the starting point precisely enough. Turns out that things aren't like that. At base, things are fundamentally uncertain, and you can never measure things to infinite accuracy. So we're doomed. Everything's all chance and probability.
If you enjoyed this clip, then head on over to Locals to access the full conversation right now. Supporters can access the video version, and everyone can access the audio-only version of the conversation. I'll see you over there.